So molecular vibration is regarded to be similar to the one-dimensional harmonic oscillator. So this is a model. Ball is bound to the wall by spring with a spring constant K. Weight of the ball is m, and let's set the axis x to this direction. Then the motion of this oscillator is expressed by this equation. Okay? Then by solving this equation, we can say energy of this molecular vibration one-dimensional oscillator energy is the discrete value. This is a model of classical mechanics, but in the case of molecules, vibration is energy is discrete and given by this equation. Frequency is given by this equation, right? And in the case of two diatomic molecules, we can set vibrational coordinate Q. Okay. So there is no spring that connects this molecule to the wall. So we consider the vibration by itself. So the displacement of each atom is defined for each coordinate Q. By setting Q properly, we can regard this vibration as a one-dimensional harmonic oscillator, and again we can say energy level is discrete and wave function is something. Okay, in this case, lambda is the eigenvalue, and this is the square of the vibration frequency. Okay, and Q is the so-called normal coordinate, and this is related to weight of the reduced mass of this molecule and displacement x. And lambda is given as a second derivative of the potential V with respect to Q. This is the general description of the molecular vibration in the case of diatomic molecules. Even if the number of the atoms increase, description is the same. So we have a method. It is shown that the potential energy is expressed as a linear combination of the multiple oscillators with the coordinate Q1 and Q2 or Q3 and corresponding eigenvalue lambda 1, 2, 3. So general expression is something like this. So even in the case of benzene, we can separate molecular vibration into 30 groups, and we can say each. So can you see? Here is some coordinate vector. So by setting the coordinate Q properly, we can say molecular vibration is potential energy is the sum of the one-dimensional harmonic oscillators. So by calculation, we can get this kind of information. What is the molecular vibration frequency? And usually, this is calculated by making a Hessian matrix, that is the derivative of the potential along with the coordinate x1, x2, x1, x1, x2, and x1, xn for each atoms. And by calculating the eigenvalue of vector and eigenvalue and eigenvector, and we get the information of lambda and q. So this is a general method to calculate the molecular vibration frequency, even in the large molecules. And today's talk, this talk is not so difficult. Practical talk. Okay, so both IR and Raman spectroscopy are the method to detect molecular vibration. Okay, so when we measure spectra of proteins, it exhibits some characteristic features. In the case of IR spectroscopy, we find amide A. This is mainly NH stretching. CH stretching here. Amide 1, this is mainly the CO double bond stretching of the peptide main chain. Amide 2, CN stretching and NH bending. Amide 3 is around here. So we find typical features like this. In the case of Raman spectroscopy, again we find amide 1 band here. Amide 2 is rather weak, but amide 3 is strong. So in this region, amide 3 appears. Okay, that is related to conformation. And we find sharp peak. This is due to phenylalanine. And sometimes we find SS bond, SS stretching of the disulfide bond near 500 wave number. So somehow we can measure the spectrum by putting the sample on the spectrometer. We get the spectrum. But in this case, in the case of benzene, we could find what is the displacement of each atom for each coordinate q. But in the case we measure spectrum of proteins, it's hopeless. It consists of 10,000 of atoms, more than 10,000 of atoms. Even if we try to calculate molecular vibration frequency, it's practically impossible. And that protein is intrinsically, dynamically changing the structure. So it's impossible to discuss the most stable structure. It's changing always in the water. That is, the analysis method cannot be the same as that for the small molecules. Okay, so we need to consider some different methods to study the biomolecules, including proteins. And today's talk is not only limited to protein samples. So let's see which part shall we watch on the spectrum. That is the matter of discussion. Okay, we find the spectrum. We find the IR spectrum, and we can detect multiple peaks like this, like this, like this. Okay. When you find the Raman band or IR absorption band, please focus on 3 features. First one, peak position. Second one, intensity. The third one, bandwidth. Okay. Yesterday, there was a question. So Gaussian, Lorentzian band. Gaussian band. There are typically 2 kinds of symmetric functions used to analyze the Raman and IR band. But anyway, these functions are uniquely specified by the parameters intensity, just a moment. Intensity, okay, peak position, width. It is also the case at given wave number. So in each case is a case important parameter is a peak position intensity bandwidth. So let's see what is the meaning of these parameters. So the peak position is related to the assignment. So peak position gives us a hint to think about the origin. So in this case, the peak IR absorption transmitter spectrum peak position is 1344, 1765, or listed here. In the Raman spectrum, we find the peaks in these positions. And here is a list of the observed peaks. So these informations are useful to consider what is the origin. And already there is accumulated knowledge that the band above 3,000 is assigned to CH stretching of the aromatic group. Okay, apart from this example, there may be a possibility that large peak appears. This is OH stretching. But because OH stretching broad peak does not appear in these peaks, so we can conclude the molecule must not have OH group. Also, here is a peak below 3,000. This is assigned to CH stretching of the aliphatic group. From this result, I can estimate that this molecule must have the aromatic CH and aliphatic CH both. So 1765, here is the large peak. It is assignable to the CO double bond stretching. So I do not explain all the peaks, but anyway, there is accumulated knowledge about the relationship between the peak position and the origin. So first of all, when you measure the spectrum, we check what is the peak position and make a list. And if possible, please measure both IR and Raman spectra. And please try to assign each peak. Then by combining overall information, we can derive this structure. There is aromatic CH, aliphatic CH, and CO double bond. And here is a strong C peak. This is transmitter, so small, lower peak is stronger absorption. And it gives evidence of the ester COOC, CCO stretching, bending. So there must be ester bond. So by checking the assignment, we can estimate what is the molecular structure. This is first thing you should do in vibrational spectroscopy. And I should mention that there is a solid relationship from to correlate the structure and spectrum. So when we know the structure, we can predict or calculate what should be the spectral pattern. So the intensity pattern of the spectrum is related to the vibrational coordinate. So how many functional groups are there? Then we can estimate at which position the band should appear. So this is some textbook, and already we know at which peak position, this is wave number, at which position, which molecule should give bands. So if we know the structure, we could find corresponding peaks. It's okay. And opposite direction is not so clear. Please remember. When we know only the spectrum, we need to be careful to derive the structure. It's because one band at certain position cannot be uniquely assigned to one vibration. That is, multiple functional groups may give the band at a similar position. So the discussion of the structure from the spectrum based on only one band is not safe. So what you should do is that when you find some characteristic band, please consider there is a possibility of this peak, this peak, this peak. And please return to this kind of table. And in the possibility A, when I find the peak around this region, there are multiple possibilities. And if the first possibility is true, then corresponding peak should appear here. If the second possibility is true, doublet peak should appear here. Okay? If you judge structure from single peak, it's not safe. Please consider corresponding other features in other peak position. If all the peaks support one structure, it's more plausible. So please get a habit to check multiple bands to conclude the molecular structure from the spectrum. So here is an example. So already spectrum of many compounds has been cleared. So here is an example. 20 amino acids are already studied. So in this way. So please, this is some example. So thorough study has been already done. Also, this is a good review to list at which peak position, which vibration of which amino acid appear. So usually I refer to this paper to check if this is, what is the origin of each peak. Okay. So, so far is discussion about the peak position. So please consider multiple peaks to conclude the band from spectrum to structure. Please focus on multiple bands. Second feature is intensity. Intensity is also an important parameter. So here is an example of two compounds, methanol and alkyl OH. Some O. I cannot count. But anyway, most molecule consists of the alkyl chain plus OH group. Accordingly, we find new OH here. And CH stretching of aliphatic group we see. It appears below 3000 wave number, so they are aliphatic CH stretching. And CH3 deformation appears here, CO stretching appears here. But you see, the same peaks appear, deformation appears here, and CO appears here. But you see, the intensity is different. It's because the number of CH groups are different. So it involves many CH groups, so it becomes intense. And in this case, methyl group appears. So methyl group gives a peak in this position. And it corresponds to these two peaks. And it mainly, methyl group is minor, and CH2 is the major group. So mainly CH2 appears here. Okay, so the contribution of OH is relatively small. So peak intensity is smaller than this case. So after giving the assignment, please check the intensity and consider the consistency. This peak should appear more strongly, but it is weak. Then the assignment might be wrong. Okay, so sometimes assignment may be the same, but the intensity might be different. It depends on the number of the functional groups. So please focus on the intensity to get good estimation about the molecular structure from the spectrum. Here is an example. Okay, they are the results of the nitrobenzene and toluene. As expected, aromatic CH appears above 3000. Aliphatic CH also appears below 3000. And these two spectra are normalized by the intensity of the benzene ring. Okay? So we can compare the intensity directly. Then intensity of the aromatic CH seem to be comparable. The largest difference is in this peak. In the case of nitrobenzene, the peak appears at 1588 and 1347. In the case of toluene, 1585 and 1379. Actually, difference in the wave number is only 3 wave number, and it is sometimes negligible, or peak position may shift depending on the solvent or some environment. So we may give a wrong assignment. So I check the textbook, and textbook says at 1588. Benzene ring gives a peak, so it must be new 8A vibration of the benzene ring. Okay, benzene ring appears also here. And 3079, it should be methyl group. Then from this result, I can assign this spectrum to toluene. Next day, I measure this result. Yesterday, I checked aromatic CH here, and there is no aliphatic CH, but this small peak might be aliphatic CH. And peak appears at similar position. Okay? Peak appears at a similar position. So, even though in the intensity different, peak position is the same, so it should also be toluene or its derivative. Then it's absolutely wrong. We should be aware that NO2 group gives large peak at this position. NO2 group gives a large peak at this position. That is, the intensity is absolutely different. They are more intense. If we know this fact, NO2 group gives a peak, characteristic peak near 1350 and 1590. Then at a glance, these two must be NO2. And intensity is different, so they must be different. But if only we focus on peak position, it's confusing because similar position, different group gives the bands. So that is, please check peak intensity, band intensity to give the proper assignment. Okay. The third feature is the bandwidth. Yesterday I explained briefly. So this is the IR absorption spectrum of H2O liquid. This is H2O vapor. Appearance is quite different from each other. Because in the gas phase, molecular rotation can be defined definitely. So we can detect the rotational transition vibration and rotational transition explicitly. So there is many ticks, and each correspond to the rotational transition. So V1 plus rotational transition. But in the liquid phase, hydrogen bonding network prevents the molecule from rotating. So in the liquid phase, we cannot define the rotational level. So the envelope is seen. I briefly explained yesterday. In the gas phase, the lifetime of the vibration rotational excited state is long enough. So we can excite the molecule to the pure excited state. And we can define which wavelength or which wave number IR light derived the molecule from the ground to excited state. So actually each peak has a meaning. This is not a noise. This is the rotational lines. So in the case of gas phase, transition frequency is pure or single frequency. And expansion frequency is defined well, so we can detect sharp bands like this. On the other hand, in the liquid phase, solvent molecules surround the solute. So water is dissolved to water. And surrounding molecule prevents the free rotation. So rotational state is not excited where vibrational excited states gradually diminish faster in comparison to gas phase. So this is when this is fully transformed, we must say transfer frequency is F plus minus delta F. So this is not pure frequency F because it finishes in a short time. So in this case, the frequency is not a single value, so band becomes broader than that in those in the gas phase. Okay. So important lesson is that I don't know what is your main sample. It may be a solution or a gas phase, but when you study molecule in the liquid phase or solution, please check typical bandwidth. Usually, bandwidth is measured at half. Full width at half maximum. Full width at half maximum. And in my experience, 20 wave number or so with a resolution of 8 wave number. And this width is determined by the lifetime of the vibration. We call it homogeneous bandwidth. Last week I discussed with a student. He found some peak with unknown noise. He assigned, this is the vibration band, this is the vibration band, this is the vibration band, this is. No, there is no possibility that you detect such a sharp peak in solution. It's because lifetime is short. We cannot find such a sharp peak that corresponds to long-lasting vibration. Okay, by calculating, by doing a Fourier transform, it becomes sharp peak. This is temporal axis. Okay. In the case of damping oscillation, we should conclude there is a width. So when you find your spectrum, please check the bandwidth and exclude. Don't say this is a vibration band. If that is too sharp, it is not vibration band. Okay. And I explained intrinsic bandwidth, homogeneous bandwidth. There is one more origin, so-called inhomogeneous bandwidth. That is due to the multiplicity of the structure. So in the case of H2O liquid, it forms hydrogen bonding, and the distance between oxygen and hydrogen, direction of approaching of hydrogen with respect to the counterpart of OH stretching is various, and its dynamically changes, not fixed. Accordingly, we find many peaks corresponding to different force constant. Okay, I don't know how many there are. Each band should have the homogeneous bandwidth, but it gathers in the limited region, and overall bandwidth is much broader than homogeneous bandwidth. So this is so-called inhomogeneous bandwidth. So if you find such a broad peak, please consider the possibility that it consists of multiple peaks. So when you measure IR and Raman spectrum, please focus on the bandwidth. Okay, this is a summary. So when you find the vibrational band, please check the intensity, peak position, intensity, bandwidth. They are useful to give the assignment and estimate the structure. Intensity is also important for the assignment and estimating structure. Bandwidth is useful to consider the origin of the bandwidth. There may be multiple structures. And we should know each parameter sometimes changes depending on the environment. So sometimes this is useful. So by changing the solvent and environment changes, then the peak position changes. From the change in peak position intensity bandwidth, you can consider what happened on the molecule, probe molecule, solute molecule. At the same time, this environment dependence makes the assignment more difficult. So please consider these features of these parameters to analyze the spectrum. And when you get the spectrum, consider these three features and ask your boss, what do you think about my interpretation? Then he will correct. In this case, this assignment is not appropriate, or this assignment is appropriate, but you didn't consider the environmental dependence. So through the discussion, you will learn how to interpret spectrum. Okay, so this is a very fundamental knowledge, but by completing these checkpoints, discussion becomes smoother. So please know these features. And one thing to get information from spectrum, one thing is necessary, that is the baseline correction. Okay, this is our recent result. I don't say what is the sample, but I measure two kinds of samples. And this is the first spectrum. It's clear. There are three peaks. And zero line is here. So baseline is not zero. This part is this intensity is given by some feature, so scattering or something. And about this result, baseline is O. So I guess fluorescence might be generated together with Raman measurement. But at a glance, you may conclude, oh, this is a good result, this is not a good result. Okay, I can get the information from this result. And I report to the boss, I failed to measure with a spectrum. Is it true? Do not give up. Okay, so when you get such a spectrum with large background, please try to fit the baseline. So this is, there is no definite way of the baseline correction. It's trial and error. So in this case, it's rather easy. So I don't know where is the baseline, but let's regard this region is flat baseline, and this part will be baseline. So I prepared blue wave by removing some data points from the raw data and prepare blue spectrum. This is also the case for worse result. So you see here is some small feature. Here is some small feature. There may be small features. Okay? Then I decided to exclude these regions and regarded the remaining part as a baseline, blue curve. So this is the baseline region that I believe. So it's important. I don't say this is a definite baseline. There is no possibility I'm wrong. No, I might be wrong. But anyway, please prepare putative baseline region. Then fit the polynomial curve. So do the fitting analysis for the blue curve. Then red line can be a possible baseline. Let's subtract. By subtracting red curve from black spectrum, low spectrum, we get first spectrum, second spectrum. Okay, intensity is normalized to the largest peak source. Intensity count is different, but it does not matter. So now baseline is rather flat. Baseline is rather flat. And you see, here is a sharp peak, 710. Here is a sharp peak, 1236. And there are two peaks. Actually, they are expected from the molecular structure. And you see, this peak corresponds to these three. And as a matter of fact, these two samples are compound A and compound A plus B. So I wanted to detect a contribution from B. So by comparing these two spectrum, I can say a contribution from A is here and here and here, and the remaining is a contribution from B. At this stage, it was apparently difficult to discuss the contribution from compound B. But by performing the baseline correction, you see, we can discuss what is the peak position, and what is the width, and what is the corresponding relationship. I said this is a putative baseline. As a matter of fact, there is a negative peak, negative peak, negative peak. I'm not satisfied with this baseline. And the main problem is that I could not measure this result nicely. So that's why baseline was somehow wavy and could not subtracted by the polynomial fitting. So the most important point is to get a good spectrum. That's true. And after getting a good spectrum, please try to subtract the baseline. Then you will find peak. It may be relatively smaller than the fluorescence background, but it does not matter. Okay? So do not give up even if you get a fluorescent spectrum with fluorescence. You have some chance to detect peak. And by getting this kind of spectrum, at least I can consider the reproducibility of each peak in the multiple experiments. Without this operation, it's difficult to discuss this peak is reproducible or not, because it's apparently too small. Okay, so this operation is common for FT-IR and Raman, so please try. So the last part is the comparison of the IR and Raman spectrum. So when I was a PhD student, I studied IR spectroscopy, and I believed IR spectroscopy is superior than Raman spectroscopy. And after getting a permanent position, I started using Raman spectroscopy. And at that time, I thought, Raman spectroscopy is better than IR spectroscopy. Okay? And someone says it equally works. So, which opinion is true? So here is a direct comparison between IR and Raman. IR spectroscopy, we detect the absorption process, Raman scattering process. Information is both, in either case, we detect molecular vibration and common, and sometimes complementary. If the molecule has the inversion symmetry, so peak position becomes exclusive. So measuring the both spectrum is highly useful. And anyway, it gives IR markup and it gives Raman markup band. And spectral window is broader in Raman spectroscopy in the aqueous solution in the study of biomolecules, because OH stretching is quite large, so it covers this region. And you know, OH bending is also large. So if the sample thickness exceeds 10 micrometer, this peak covers all, and transmitted light intensity becomes close to 0. So IR spectrum, we need to be careful to measure IR spectrum of the aqueous solution samples. In that sense, Raman band of the OH bending is not very strong, so it may be useful. But the advantage of the FT-IR is that horizontal axis or wave number is correct, very accurate, because this is measured by the interference of the helium neon laser. So there is a method to determine the frequency very accurately. So accuracy of the wave number is correct. This is the advantage of FT-IR spectroscopy. In the case of Raman scattering, we need to measure indium or some standard light, standard lamp, and we need to convert a CCD channel to wave number. In the IR spectroscopy, we detect the inner product of the electric field and transition moment square. In the case of Raman, as we learned yesterday and today, it is related to polarizability. Okay? So when we use a polarized light, polarized IR light, we can directly discuss the inner product of the IR polarization and direction of the vector of the transition dipole moment. So parallel or perpendicular and absorption intensity changes. In the case of Raman spectroscopy, all we can do is to measure depolarization ratio. So some combination of the 9 components of this tensor gives the invariant quantity G0, GS, GA, and we can discuss the symmetry group of each vibration from this depolarization ratio. When we combine IR spectroscopy with microscope, what is the spatial resolution? It is limited by the diffraction limit, and probably 25 micrometer is the smallest area. On the other hand, when we combine Raman spectroscopy with microscope, it is nearly equal to or less than wavelength. Quite different, and the spatial resolution is much better in Raman microscope. And vibrational spectroscopy is frequently combined with time-resolved measurement. Temporal resolution is owing to the response of the detector in the case of time-resolved IR spectroscopy, and by using photovoltaic MCT, it is 50 nanoseconds. This is the kind of best value. On the other hand, using Raman spectroscopy, we can use the visible light and pulse laser. Also, we can prepare some fast detector, strip camera over optical gate or something. So the temporal resolution is picosecond. So in the case of IR, the advantage is about the polarization measurement. We can discuss the direction of functional groups with respect to the alignment axis. This information cannot be derived from Raman spectroscopy. On the other hand, using Raman, we can utilize resonance enhancement effect. Resolution is higher, spatial resolution is higher, temporal resolution is higher. So they are the advantage of the Raman spectroscopy. Also, both techniques are readily combined with additional techniques. In the case of IR, attenuated total reflection technique is available. Diffuse reflectance measurement, reflection absorption spectroscopy, photoacoustic spectroscopy, IR emission spectroscopy, or combining with gas chromatography or liquid chromatography, it's possible to use IR absorption as a detecting method. Microscope, time-resolved spectroscopy, and modulation spectroscopy. With the Raman spectroscopy, we can use resonance effect and selective detection of the chromophore in huge molecule. So sometimes surface enhancement, Raman scattering is utilized to enhance Raman signal. Also, nonlinear Raman spectroscopy gives the clear peaks, CAS, SRS, like some nonlinear spectroscopy is available. Also, Raman is also available as a detector of the liquid chromatography, microscope, time-resolved spectroscopy. Okay, so this is the comparison of IR and Raman spectroscopies, and each method has each advantage. So first question, someone says IR better, why not? The other guy says Raman is better, why not? And someone says it must equally works. Okay, so in my impression, previously I was this person, and now I'm this person, or I'm this person. So modest, most appropriate conclusion is case by case. Okay, so please understand what is the advantage and disadvantage of each method, and please choose proper way for your sample and for your discussion. Okay, so this is the slide I prepared for this talk. Okay. Any question?
So my question is about hyper Raman. So since hyper Raman is so weak, so why do we use it? Like, what's the applicability of hyper Raman?
So I'm planning to explain in the fifth day. So usually, as hyper-Raman spectroscopy is not so popular, honestly speaking. And I know 5 groups in the world is now publishing the hyper-Raman papers. And so it is much smaller group number than IR and Raman. So, but the reason is because hyper-Raman signal is very weak and difficult to detect. But it has its unique information. And so if the measurement of hyper-Raman spectroscopy becomes much easier, then larger number of groups start to measure, I think.
Okay, sir.
Sir, which spectroscopy is better to detect the interhydrogen bond or intrahydrogen bond?
You mean intermolecular hydrogen bond?
Intramolecular hydrogen bond or interhydrogen bond?
I'm not sure if there is a difference between intramolecular and intermolecular. So I don't have a general answer.
Okay.
So in the case, so there is a possibility if the hydrogen bond is intramolecular,
Yes, sir.
then the structure might not be so flexible than intermolecular one. So width may be different because of the less variety of the hydrogen bonding structure.
Okay, sir. Thank you.
But it depends, I think.
Thank you, sir.
Okay.
Excuse me, sir. Yeah. So I have one question that in the peak position slide, so you can show it once. First slide, maybe. Yeah. Yeah, here you can see that some bands are present in IR, but some bands are not present in Raman. So is there any specific reason for that?
So it depends on the vibration mode. So if the molecular vibration changes the permanent dipole moment largely, then it should give the large absorption, and vice versa. If that does not affect the dipole moment, intensity should be small. And intensity of the Raman band depends on the polarizability. So the origin is quite different.
Only the intensity changes. The band is present in Raman also, no?
Sorry?
So band is present in Raman also, but only the intensity is changing. Okay, so there is no band position is showing there, so that's why I'm thinking that it is not present in Raman maybe.
Too small to detect.
Okay.
So in the case of lower symmetry, all the peaks should appear in both spectrum. And when the symmetry is higher, and in particular, if molecule has an inversion symmetry, then the peaks bands that appear in IR does not appear in Raman, and the peaks that appear in Raman does not appear in IR. So that is already shown. But in the case of lower symmetry molecules, there may be, but too small to detect.
So another question is about the band intensity. So when we are targeting any liquid sample, so the focal length continuously changing upon irradiation. So when we are adding something into a solution, so how can we detect, how can we check the intensity difference between the two solution?
It's a difficult. So you mean due to the difference in the refractive index, focal point is different. So
no, maybe during the experiment. So if in case of solution, we are using cubet, or we are using in a glass slides, we are just drop the sample and try to focus it. So when we are having two different measurement, so maybe the focal length changes at that time. During the focusing of the sample, the focal length maybe changes. So how can we compare the intensity of that two liquid sample?
So please control the condition of the sample to make it identical. Okay, so that is a kind of artifact. So condition of the sample is changing, then the intensity changes. You can avoid such a situation.
Can't we do by baseline correction or something?
Sorry?
Using baseline correction, can we compare it?
So in that case, so first of all, if I try your experiment, I should pack the sample into some glassware or something to avoid the evaporation. Then measure. Then the sample volume does not change and focal point does not move. Then by that kind of effort, the quality of the data should be improved more. Then after that, by solving the major problem, minor problem may be solved by baseline fitting or some additional mathematical procedure, numerical calculation procedure. But so the first priority is to get a good spectrum. Okay. So if the quality of the data is not very good, we must make an effort to make it better.
Next question is from this graph. That here we can see there is 3 peaks are there.
Sorry?
3 peaks are there at initial. Yeah.
Yep.
Yeah. 3 peaks are there. There is 3 peaks.
1 or 2 or 3 or.
Yeah. 400, 500 maybe something. So after baseline, the peak intensity and the sharpness of the peak changes after doing the baseline in the last graph. Yeah. That one.
This graph?
Yeah. These 3 peaks are sharp, and after doing the baseline, it becomes, the sharpness becomes gone and the ratio also changes. The band ratio also changes. So why does it?
Ratio of 3 peaks changes, you mean?
Yeah. These 3 peaks after doing the baseline.
I don't think so. So this is the largest.
Yeah.
Largest, second largest, third largest.
Yeah.
And this is also.
So after that, the below.
Below?
Oh, okay. These two are different. These two, this one and the below one is different. Maybe this. Yeah.
This spectrum?
Yeah, this spectrum and the above spectrum, those two are different.
You mean intensity of this peak and this peak and this peak?
Yes, sir, yes.
So again, this is the tentative baseline correction. So I should repeat the experiment, and even if I get a better spectrum and the result is the same, then we should discuss why intensity is different. And if this changes, then intensity should be the same.
Okay. Thank you, sir.
So we finish. Then this is all for today.